Oh, I forgot to print the seminar sheet. Probably everyone has.
Yeah, that is-
There's the planet.
yeah. Okay. So there's some messages. Let me check. No. So, yes, let us start. Okay, I understand that previous homework, nobody answered a question about NP completeness of disjoint cycle problem. Nobody could answer, so I will some point post the answer for this problem. And then in the last homework, there was this degree missing. I don't know, was it you who told us? I forgot the name.
No,
Yeah, so the second homework. And I promise I changed the homework problems, just the second about Pavel is a little bit different, mostly difficult to understand, but I changed it to a much easier problem so that the marks will be higher for the homework.
So which problem did you change?
Just for the seminar that's in an hour, I changed, yeah.
Okay.
Yeah. Yeah, just to be sure that there is a question that everyone has right, I removed this problem and put in as first problem something about so checking that multiplication is in NL. Okay, but let's start with the lecture. So yeah, the problem was that I asked for the grades of the homework, but it came only like yesterday. And then I didn't see that something was going wrong. And I had to decrease a bit the difficulty. Okay, but yeah, homework is for training, so it's no problem. Yeah.
Where do you take the tasks for do you create them yourself? Or?
Yeah, I need to invent them. because I cannot go on the internet for the task because you do the same thing. So, and that's the problem. Like I need to find easy enough question, but then it's not so many difficult questions. It's easy to invent, but so that's why the teacher is tempted to make harder question, because like it should be easy, not on the internet, but it should also be like meaningful. Like you want to think that, oh, this is a problem, it can happen, or it's natural, and all of three is each year more difficult because each time more people put their homeworks on the internet. Okay, but let's do the real class now. And so the space complexity. Today we will speak about can we solve problems in certain space, and this is very interesting when you deal with dynamic systems. So we will speak about PSPACE completeness. And when you have to deal with the game, it's either NP complete or PSPACE complete. So there is this very nice game called Sokoban. It's where so there are a bunch of Sokoban means warehouse in Japanese. So you have a little guy and you can push against some stuff, and I think you need to move out all the stuff of the house, but before you can push. So it's example of PSPACE complete problem. So if you want to have it solved by an algorithm, so space is much more powerful resource than time, because space you can reuse. Polynomial space means that polynomial amount you can reuse, but we already spoke about it. But that means if a problem is PSPACE hard, then your life is you will need to work hard to get. It's not a good sign. Like if it's NP complete, it's like all the research in companies. I mean, not all, but let's say a lot of research in company is how to deal with NP completeness, and there is always some technique. Eventually, people correct the problem, and if not, set solvers can bring you pretty far. But for PSPACE, it's not true. So, okay, and in theory, if you have set solvers, you can call it many times to solve it. But when you need to call a set solver many times, you will see that it's still not magic. Each time you need a second or something. And okay, but this is again philosophy. I should speak about mathematics. And we will also speak about logarithmic space. But how can we speak about logarithmic space if the input is of linear size? By definition, the length of the input is this parameter n. So how do we define it? And for this, we use a two-tape Turing machine. And so there is one special tape for the input. So there is an input tape and a work tape. And on the input tape, the machine is not allowed to write. It can only read from the input tape. So here we have the first input and so on. The last input then followed by infinitely many blanks. And then there is a short work tape. So okay, in principle, the work tape is infinite, but the goal is to when we define L space of log n, to just use order log of n space on the work tape. So L is the set of all languages A for which there exists such a Turing machine. So there are two computation heads. Such a Turing machine can be decided by such a Turing machine in which there is never written on the input tape, and on the work tape at most order log of n cells are used. So that is example of a language that is in log space is addition. So the input So there is a language where we get two strings split by some separator. And so A and B are integers in binary. Sorry, we need three of them. And the question is whether A plus B equals T. So this language is in L. So how can we check it's in L?
Symbol by symbol.
Yeah, indeed. So we will perform addition of A and B. We just need to remember the carry bits, and it's all one information. So this is in log space. NL is non-deterministic log space. Okay, there are two definitions, one with certificates. Well, from NP, we know that there are two equivalent definitions. Here, definitions are no longer equivalent. Be careful with this. It's source of mistake in research and computational complexity. Here, we need to use non-deterministic machines. So a problem is in NL if there exists a non-deterministic machine of such type, so just a machine with two transition tables in the computation head that decides this problem. The thing is that the machine can make a polynomial amount of, okay, but by the way, so we have L is a subset of P, right? Because we only have a logarithmic amount of space.
Okay.
So then if we encode all configurations, let us think for now, let us make life easy, and let us assume machine is not allowed to go at more than 1 bit by on the input. So then a configuration of a machine is just a state of the work tape, positions of the two computation heads, and the state of the machine. And that means that, so the number of states we have is 2 to the power order log n for the work tape times the two positions of the tape, which is like n log n, order n log n. So here we have n for the first position of computation head, order log n for the second one. And then the size of Q, but that's a constant. The number of states of the computation head. So this is poly of n. If the machine has a polynomial number of different configurations, we know that if it computes longer than this polynomial plus 1, it is in an infinite loop. So we conclude that L is a subset of P. It's the same proof when we said P space is a subset of X. Okay, and why I'm speaking about this. So
did
for
you prove that the space is a subset of X in the lecture?
I forgot it.
I'm not
I
sure
thought
that
that-
the space is subset of X.
Seriously, I skipped this one.
We
Oh,
started
okay.
at P is a strict subset of X.
Yeah. This I know. Okay. Oh, that's good. Yeah. Okay, but then you understand it now. P space is a subset of X. So yeah. So we have P space is NP is a subset of P space, and this is a subset of X. So, and each inequality is a big important open question. So it can be that P equals NP. It would be great. Then, if this is reasonable polynomial time algorithm, whenever you have this hard optimization problem, you run polynomial time and get perfect answer. So that would be great. If NP is equal to P space, it would also be great. I will spoke about these games. There is Sokoban, but there are also certain versions of chess. It depends on termination rules. So if you apply 50 moves rule, then chess is P space complete. Go also like with one of the versions to resolve Go, is that you cannot do 3 times the same call attack after each other or something. Okay, I forgot a little bit the detail.
They're going to chess and checkers.
They're all PSPACE complete, but you need to talk about the generalized version, because on the fixed board, you know that the first player has winning strategy. I mean, it's just a finite problem. So the generalization for chess is, yeah, for chess, you have n by n board, and you can have any piece any number of times on the board, and you need to decide which play, sorry, any piece any number of times, but the queen only 1 piece. And if the queen is taken, the game is finished. The king, of course, yeah. And yes, and so with the 50 moves rule, this problem is PSPACE complete. And if you say that, there is another rule, I forget which one, like you cannot repeat a game state or something.
No, chess is just a 50 moves rule about the taking of the pieces, and I think it's all.
Well, yeah, people analyzed it with the rule that you cannot repeat a certain state.
It's just in chess there are rules that if you 3 times repeat the moves, then it's a rule.
Yeah. But with this rule and not the 50 moves rule, then it's exp complete. So it means it's an exp, and every problem an exp reduces to it. And this illustrates why already this small game with 8 by 8 is so difficult, because like the asymptotic version of problem is much harder than NP complete. Okay, so if NP equals PSPACE, it means that maybe solving chess is difficult, but at least if there is a winning strategy, there is a compact way to represent it.
Compact in polynomial space.
Yeah, in polynomial space. Now there is no way to represent a proof of a winning, so that the winning strategy works. So if such proof exists, then PSPACE equals NP.
I have maybe not so useful question, but for me it was always ambiguous. Why are when we started talking about space complexity, why are we changing the notation from like for time complexity, we have P as polynomial time and PSPACE as polynomial space. Like about the logarithm, we have not a logarithm time, but logarithm space. Why don't we do it like that? Why don't we use L as a logarithm time? Well, just d time on.
Yeah, logarithmic time is a bit strange. Then you don't have time to read the input. So, okay, it's studied, but then we need to modify the problem, use probabilistic algorithm. So there is a field like this called property testing. And yeah.
So it's just
it's just because these classes are way more important than the time versions. Okay, so that's 3 months. So we spoke about yeah, PSPACE, yeah. Oh, yeah. This, yeah. So this is the union. PSPACE. This space.
I asked because and in N space means that the machine is non-deterministic, but P in PSPACE means that we have polynomial space. So we can probably have NP space, yeah.
Yeah, indeed. And PSPACE also exists. And we will oh, I forgot one of the goals. So here after this I will prove that PSPACE equals NPSPACE. So this is one of the beginning of the field. People quickly realize that P versus NP problem for space is already solved. It's because space is more powerful. You can reuse the space and you can deal with non-determinism.
Was this problem P versus NP space like the problem P versus NP time? So was it difficult at some point of time?
I think they started with P versus NP, and then they say, okay, it's too difficult, let's try similar problems. And then somebody asked it, and I guess somebody else solved it. Yeah. And we will explain the proof. Okay, but we are now thinking about these relations. What happens if PSPACE is equal to X? It means that if computation takes very long, you can do it in small space, in reasonably small space. So,
Not like not true.
yeah. Well, there are so many algorithms and so many algorithms that were not studied yet. So yeah, they're completely crazy algorithms, like with huge implicit constants. So you might learn about this whole story about graph minor theorem. So there are a huge number of properties you can check in cubic time, but the constant in front of it is gigantic, like a power of exponentials, yeah, of twos, and so completely useless. And it took like a career of two enormously clever mathematicians to prove this theorem and come up with this algorithm. So that there might be some surprises that in theory these are equal, but in practice it's not the case. Okay, so yeah, but for now we don't know it. But okay, this each time a nice news, speeding like doing large long computations in reasonably small space. But we cannot have all three equalities at the same time. We already know we cannot have three good newses at the same time.
So something isn't.
Yeah, because we know that P is a strict subset of X. So this was easy to prove. It was in our first lectures. So one of them for sure must be a strict inclusion.
News probably.
Yeah, but most people think that this.
Everything.
Yeah. So I mean, of all 8 possibilities, people agree that this is the most likely. But that doesn't mean that. But specialists refuse to speak about individual inequality. If they say you will gamble on it, they will say, no, I'm not going to gamble because I really don't know. So, and then if we force them to gamble, they will do 50-50. But in practice, we need to assume they're different because we don't have the algorithms. And if somebody claims to have them, then ignore it because unless it's a famous guy. So there are conferences, Stock and Fox, and you can check his papers. If he has papers there and he says he can solve one of these questions, maybe you can listen to it. Like if he's 10 papers in such conference, but I have 0 in such conference. Yeah.
I actually once found a paper claiming that they've proven that P is equal to NP. So it was.
Oh yeah, but there is a list like with 70 papers that claims that P is equal to NP and 70 around. I don't remember something like this. That's different from NP.
Yeah, it's I've been taught that it's a useful question when you're trying to prove something to check whether it implies that P is equal to NP, and if so, that's you probably have a mistake somewhere.
Yeah. 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 So please, if you have written such papers in these important conferences, then you can start then you can maybe assume, but I find if I make this conclusion, it doesn't take much time to see my error. So for me, it's yeah, the problem with these papers is that the people who write them are not even at the level where they can see mistakes. And yeah. Okay, so yes, let's now speak about another problem in NP, which is reachability, directed reachability problem. So we're given a graph, you can code it by adjacency matrix. Yes, adjacency matrix. 2 nodes, is there a path from S to T? And so this problem is in NL. So why is it in NL?
Well, we can just yes.
Yeah, the path.
Check on the logarithmic space, like just plain attributes.
Yeah. So the machine starts in S and then uses the 2 transition tables to guess a neighbor of S, and then go to the next node, and then writes down index of neighbor and binary using and so on. Okay, so directed reachability problem. There is a variant of this problem, undirected reachability and undirected graphs. And so there was a nice surprise. This problem is of course also in L for L for the same reason, but somebody found a clever algorithm that is in L, Rheingold, in 2000 something. So, but this is a difficult algorithm. Okay.
In L?
Yeah. This problem for undirected graphs is in L, but for directed graphs, it's probably not in L. Because if it, people have proven if it's in L, then it is, then L equals NL. And that means NC1 equals AC, enormous amount of consequences, famous open problems that are solved. So, okay, if you think that you can prove NL equals NL, the same story as we said for this open problem, you probably made a mistake somewhere. Okay, so now let us prove that directed reachability is in space log squared of n. So this is a deterministic class. So let us write the theorem, or maybe proposition. Oh, okay. So reachability is in space log squared of n. Okay. And the algorithm is called middle first search.
Now we're talking just about the plane, we should go to not
yeah, directed reachability here. So yeah, by default, reachability is directed. Okay. Yes. So so the input is a graph, and we want to know whether two nodes are connected by directed edges. So, and we had an exercise like ladder problem, like find the ladder, and there you also had to prove that it is solvable in polynomial space. And there you apply the same algorithm, the middle first search. Well,
nobody
solved it. Yeah. Okay. So how we're gonna solve it? Well, it just we will solve that by recursion. We will solve a stronger problem. So let us have an algorithm. So I will middle first search. So you get two nodes, U and V, and T is some number of edges.
What is the middle first search?
Middle first search. So I will tell him. So the input is two nodes and a number. And the answer is yes, if node U, and there is a directed path from U to V of length at most T. So exists path of length at most T from U to V. So that's the answer.
Like Lloyd algorithm, I don't remember some algorithms, quadratic complexity of path length searching.
Yeah, so it's solvable in linear time on RAM model, word RAM model. But we don't care so much about time now. We will care about space, and we want to aim at logarithmic log squared space. So algorithm will be a bit different from algorithm scores. And then the algorithm will be just a for loop. Oh, wait. If T is at most 1, then it is easy to check answer directly. So just return answer directly. You just need to look up to the end. Well, of course, we're also given graph as input. So let us pick, I mean, the graph is fixed here, G, and the graph is written on this special input table. And so if T is 0, then we check whether U is equal to V. If T is 1, then we check whether there is an edge from U to V.
You mean that when you say the graph is on the
Yeah.
special table, you mean the input table?
Yeah.
Okay.
So when we eventually implement it, so when I say fix G, we just assume we can read the graph. And so then this algorithm can just in one step without using any memory, it can answer. And then otherwise, direct answer, so return answer. And then the algorithm is finished. And then otherwise there is a for loop. We will iterate over another node. So for W in the vertices of the graph. The graph consists of vertices and edges. So for every node, we will check whether there exists a path from U to this node of length at most T over 2, and another path from W to V, also at most length T over 2.
So it's just something like algorithms meet in the middle.
Yeah. So we return Fs of the same graph of U W T over 2. We will round up in case T is on, and yes, and let's make some space. Okay, or I continue on the next line. And Fs vertices E of W V length T over 2. Okay, so this is our algorithm MFS UVT. And so this is recursive algorithm. And to know the answer of reachability, we will call it with T being the number of nodes. So our answer, so this is solved by MFS on the graph, S and T, sorry, here is our problem, T and the size of the graph here. Because the length of every, if there is a path, if there exists a path, then we can assume it has length at most T. So here is description of algorithm. It's clear that it works and that it solves a problem. This is kind of obvious. Okay. Now we need to check how much space it's using. So what do we need to store to execute this program? So it's recursive program. It makes 2 recursive calls. But note when it makes the first recursive call, after doing the first recursive call, the space can be cleaned up and the second recursive call is done. So we just have to check the depth of the recursion stack and then multiply this by the maximal size to store 1 recursion stack. So you know all this. If your program crashes, you see all the functions that are nested. And so this is recursion stack. And so we can use it to this concept to check how much space it's used. Because at any moment, like the program itself, without the recursion, uses polynomial space. So what do we need to store? Just the variables. And the variables, sorry, logarithmic. And the variables take logarithmic space. Right? So just the program itself without recursive call uses logarithmic space. And recursion depth. So what is recursion depth?
So logarithm for size of,
yeah, size of the graph. So we have so space for just the main program length n times the recursion depth is log n. So order log n times order log n. Well, the recursion depth is exactly log n. So we have the space is precisely log squared of n. And so we have proven that direct reachability is in space log 2n. Okay. And the corollary of this result is that P space equals NP space. So let me remove this proof. Unless there are questions, because it would be stupid if I delete the proof and then I have. But please, well, actually, I should not remove but I have not enough space. This program will be important later, so please store it carefully in your memory. We will need it to prove that TQBF is P-space complete. The TQBF will be like 3 sets for NP completeness, a really important problem. Okay.
Can you repeat why is this a proof for P-space equals NP-space?
I still need to explain this. I'm just making space, and unfortunately, I need to delete this nice program. Okay. So now let us prove a corollary. P space equal to NP space, and it follows directly from configuration graph. So what's configuration graph? It's a graph. Every node is a configuration of Turing machine, and there is an edge from one configuration to another configuration if the machine goes there in one computation step. So note that, so what is NP space? NP space contains non-deterministic machines that use polynomial space. That means that for every state, there is 2 outgoing edges, because we can go to 2 configurations depending on the graph. And so we have a reachability graph for Turing machine. Now let us make a machine that cleans up deletes a state and goes to the first cell and halves. So now we have, we know that if the machine accepts, then he cleans up everything and goes to the first state. If machine rejects, then, okay, you don't need to do anything. And that means that in this configuration graph, we can understand, how can we understand that the machine accepts its input? If it accepts the input, then there is a way for the machine to go from initial state to this unique accept state. There is a path. If machine rejects, it means there is no such path. And that means checking whether machine accepts is solving reachability problem.
On the configuration.
Yeah, on the configuration graph.
All we need to understand is how big
this configuration graph. Okay, well, while I write down this theorem and the beginning of the proof, you can think how big is configuration graph. P space is equal to.
Well, we pretty much need to count the number of states, and if some states is repeated, then we are on the loop. So the size of the graph is bounded from upper bound is just the number of states of
Yeah. Okay. In your explanation, you are giving 2 different proofs at the same time. No, it's okay, but I need to be clear. So let us go step by step, that the others are not confused. So, in the proof I just tell, and then I will speak about his second proof. So the proof that I tell, we need to know the size of. We will run our middle first search program, and the graph will be configuration graph of the machine. So how big is this configuration graph? The configuration of machine consists of 3 things: contents of the tape, position of the head, and the state of the head. So we need to multiply these 3 things. So number of configurations of the head, again, the same thing. The number of states, so the position of the computation head will be poly of n, because the machine uses polynomial n of space. So that's the number of positions we can use. So that the space, so we have a machine that runs in space P of n, So P of n plus in space less than P of n, because we can have one more cell. No, sorry. We have a machine that runs in space P of n, so P of n is the maximal position. Yes. And then the cell, the tape cell, which is the contents of the tape, which is the size of the alphabet to the power P of n, because we know everything after P of n consists of length. So that's the number of states. And so we have the size is bounded by 2 to the power order, so 2 to the power P of n. It's exponential size.
Can you repeat again? The Q is just we choose the position for
no, Q is so a Turing machine consists of 5 tuple. Q, the number of states of the head.
States and the,
tape alphabet, transition table, Q0, and
we pick the position for the head. Second, it's just size of
the contents of the computation head, and we did it already many times. So we know that this is of the form 2 of n to the power c. So, for some constant c, that's the space that we use. Now in this result, so reachability is in space n, we need to replace this n by this thing, because the input of reachability will be, the input size of reachability will be this thing. But then we get log squared of 2, so what we have is space log squared of 2 to the power n to the power c. And this is equal to 2 to the power, big O notation. And then this is equal to 2 to the power n to the power 2c. And so we use polynomial space.
One more time. Where did we get to? So the size of the alphabet is
Okay.
the size of the alphabet
Is a constant. So machine is fixed, doesn't depend on the input.
Yes, but we have this number of states Q and this.
So Q is also a constant. This is a polynomial. This is also a polynomial. So we get for configurations, number of configurations, 2 to the power n to the power c.
Okay. So the polynomial disappears.
Yeah, because we have a logarithm. Yeah.
Okay.
And then we get basically polynomial squared.
Okay.
Okay, and that means we have proven that PSPACE equals NPSPACE. So this goal is finished. Now I have 40 minutes. That's very good. TQBF is PSPACE.
you wanted to talk about the second proof.
Yes, your second proof. Well, your second, what you're doing is you are thinking about this problem.
Yeah.
And you say that the runtime here, you are bounding the runtime of the Turing machine. And so you were directly inserting the value here. You were saying, okay, we know that the machine must terminate in a certain time.
Yeah.
So we only care about paths of certain length. So you inserted the time bound here, and then you carry through the analysis. So you start to go through the proof I just explained of this theorem, but with this time bound, which is also a correct way to prove it.
Yeah, we
But,
just use reachability, but instead of the just for the length of the path, we are using what?
The runtime. Well, there are two things. Either you use the theorem or you modify its proof. It's two different ways. I mean, very closely related, but you were kind of you were modifying the proof of this theorem.
Yeah,
but I wanted to speak about the direct reduction from this theorem.
Yeah, okay, but what would be the runtime in the second case? Well, the runtime of machine we want to bound by what? By Polynomial.
Yeah, the runtime will again be exponential. And the runtime of both proofs, because it's basically the same algorithm. Yeah, but
okay.
in principle, your algorithm has a chance to be a little bit better because you don't maybe not okay. Okay, note that in this proof, there is this question like we need to construct the configuration graph and it's exponentially big. And we don't have, then it's, so this algorithm, like when we transfer the graph to this problem, we don't have the graph as the input. And so there is, it's kind of cheating because we first need to create this graph and then run the algorithm. But note that this configuration graph has a very simple structure because every node is just a description of a configuration. So when we store one node, storing one node is okay, and knowing all the neighbors of a node is also okay. The two neighbors, to construct them, we just look to the two transition tables, which are fixed, and we can write down the two neighbors. So when we run this algorithm, there was a recursive algorithm. What am I talking about here? Well, I'm talking about the first step when the distance is at most 1. We don't need to construct the full configuration graph to know whether two nodes are the same or are connected by an edge. And the other step is just make an iteration over all nodes and apply recursion. And so for this, we also don't need the graph.
So you mean that we just we not construct the graph, the whole graph, but we are just looking at the part of the graph, which is reachable from our state.
Yeah. So to run this algorithm, we don't need to. We can use implicit representation of the graph. I mean, we can, given two nodes, we know whether they are connected by an edge or not. And that's the only thing that's needed. We don't need to have to store this graph explicitly in memory. So, okay, maybe I'm right. I should speak about this algorithm and not directly use the statement. Okay. So, yes, then we have proven this, and we have proven this. So now we will go to problem TQBF, which is a bit like TreeSat for NP completeness. So a lot of reductions go from TQBF. So what is it? I think I can remove this. So TQBF stands for True Quantified Boolean Formula. Input Boolean formula. Quantified Boolean formula. So what is quantified Boolean formula? I will give an example. So there exists X for all Y, there exists Z, such that, and I prepared some example that's hopefully interesting. So Y or Z, and not Y or not Z. And X or Y or not Z, and X or not Y or Z. Okay, so here is so all variables, they range over 0 and 1. X, Y, and Z have binary values, of course. And so now the question is this formula true or false? So what do you think?
So given X, Y.
Yeah, so they're quantifiers over X. So basically, you must say, does there exist an X such that for all Y, there exists a Z such that this thing is true? Okay, I will help a little bit. Maybe it's difficult, or maybe somebody knows the answer. So note that, let's look at Y and Z. So Y and Z appear in all 4 ways in the formula. So when we ignore X, we see y not z and not yz. So it means that whatever assignment we give to y and z, always one of the four will be false. So how can we rescue the situation? We can rescue it by setting x to 1. Then these two clauses are true, and we only have to focus on these two clauses.
But we don't have an X in these clauses, so if one of them false, then
No, but it's clear what this means. There exists x. So if we want to prove it's true, then we can choose x.
No, I understand, but we don't have an X on first and the second clause, so.
Yeah. But when we set x equal to 1, so x, if we want to prove the formula is true, x doesn't appear with negation, so it's clear how to choose x.
I understand, but it's not enough that we just.
Okay, let me continue. So these two are already true. And then we have to make sure that these two clauses are true. X is not there, so we for every y, there must be a z, so that at least one of these clauses is true.
Why at least with both of them we have a conjunction. So
Sorry, we need to find the value z so that both are true.
So V has to be just different
From y, yeah.
So we have a direct algorithm how to make it from the.
Yeah, indeed. So we understand that this formula is true because we set x equal to 1. So this should be 1, and z is equal to not y. Okay, that's the proof that this formula is true. Yeah. Okay, and so TQBF is this problem. So you get the quantified Boolean formula, so it's formula in this form. And the question, is it true? Okay. And so now there are two questions we have to answer. We want to prove that it is p-space complete. What does it mean? It means that the problem is in p-space and it is p-space hard. Every problem in p-space reduces to this problem.
We probably discussed this earlier, but I don't remember what are the requirements for reduction from
polynomial time reduction. Sorry, yeah, I didn't say it. Yes, you're right. So for every problem in p-space, we will need to make a reduction to this problem. So basically, for every Turing machine, we will need to check with the formula whether the Turing machine accepts. Okay, but this for later. Let's first prove that this problem is in p-space. So task 1 in p-space. So how can we prove this? So someone? Yeah.
I'm not sure if I can do the test correctly. So you've given an example, but the formula may look different.
Yeah. So the problem is like this. There exists x1 for all x2, exists x3, and so on. And then in the end, for all x to n, let's say that's even and it's alternating. And then we have phi x1, x2, x2n. So that's the input. There's a quantified Boolean formula. We get a list of quantifiers for all variables and then a Boolean expression.
Can't we just go begin from the end and go to the first quantifier and check?
Okay, so you say that let's try both values here.
Yeah.
And then I guess you want to make a recursive program.
Yes.
Like it's true. Okay, I will write it in this mathematical sloppy way. where I define a variable with the variables inserted, a function with the variables inserted. Oh, sorry, I need quantifiers. Is true. There exists x1 for all x2 and so on. But actually, I should have, let's make it more general.
What is Q?
Q, so Q1, Q2, Qi is just an element of there exists for all. It's quantifier. This is our input. Q1, Qn, Xn, fine. And so here we view this thing as a string, not as a value which is 0 or 1. So it receives a description of the formula. And then the proposal is to make a recursive formula. So there are two cases. If n equals 0, it means there are no variables. And here we just have a constant expression. Then we evaluate it. If n equals 0, return evaluation of phi without arguments. And otherwise, if q is equal to for all, then return by 0 x2 till xn. Okay, I need to write quantifiers as well. So now the string boring me 2 qn xn by 0 x2 till xn. Okay, and I forgot to call the function. It's true. And it's true. I think it's quite clear. Q2, x2, qn, xn, phi of 1, x2, and xn. And then, and otherwise, if q is equal to exist, sorry, q1 is equal to exist.
What does mean the quotes?
What?
The quotes.
The quote, it means that's an encoding. Otherwise, if I don't write the quotes, it's either number 0 or 1, if it's true or not. Like then in your mind, the formula gets evaluated and the answers appear. So we want the description of formula.
Mm-hmm.
So it's maybe better to write it like in Savitch, means encoding of. Okay, that doesn't matter. It's clear. But let's, otherwise, I have to change the formula. And then here, return it's similar. Okay. So, what is the space of this formula? How much space is used?
So the space for each x and q is logarithmic.
Is
For
linear?
each x, n log n. N log not n, but size of thing.
Yeah. So we have n recursive calls, and each one is order size of this expression. And there, now I'm using n for number of variables and input. So it is input length times n is a bound on the size. And so, of course, it's polynomial in the input. So we have proven that this problem is in PSPACE. Now, that was easy. Now let us prove that it's PSPACE hard. So I'll remove everything. We don't need this anymore.
Then you have to make the end of the
Okay.
yeah, about well if quantifiers equals exists
Yeah, but then the same with or, of course. Yeah.
So we can.
Yeah. Yeah. So PSPACE hard. For every A from PSPACE, A polytime reduces to TQBF. Okay, so A is in PSPACE. So let us have a machine. Let's also use another marker. Yes.
Can I ask a question
Yeah.
about that algorithm? Am I right? For each of the quantifiers, you will make another branch of the like a graph of recursion.
Yeah, indeed.
So
It's game 3.
but isn't the number of leaves exponential? No?
Yes, number of leaves is exponential. But to bound the space, know that after each recursive call, we free the memory. So what you're saying is that, okay, so note, good questions, by the way. So this is equivalent to a game, right? So if there is a player who wants to prove it's true, he must come up with X, and then opponent can choose Y to make formula false, and then we have to answer with Z and so on. You can view it as a game. What you are saying is that the game tree has exponentially many leaves. But when I don't know whether you learned this in algorithms course, when you go through game tree, you only need to store the branch. Yeah. So you will indeed need exponential amount of time to check to go through this. So in the game tree, you have this exist nodes and for all nodes. Imagine that you want to check whether the exist player can win. So then here will be, he will take the OR. Yes, OR. And then here are nodes corresponding to the other player. So we need to make sure that the first player wins for both nodes. And here we have OR again. And let's say that then the game is finished. So here we say first player wins, first player loses, first player wins, first player loses.
We need to store not more than logarithm space.
No, polynomial space. So we prove that there's in P space, not log space.
Wait,
Okay, but let me first explain what is game tree.
oh yeah.
It's the same way as another way to view the algorithm. So the game tree says that, okay, here we have a bunch of answers in the leaves. So game tree takes an OR here. That means that becomes 0. Oh, that's not interesting. Here we also get 1. Here we get 1. But here we get the 0. It means that here we get the 1. And then we see that here we get the 0. Yeah. And here we get to 1. So we know that the first player wins in this tree. Okay, and to traverse the tree, we can just go do it in that first way. Because when we go up, we don't care about the other branches. Yeah.
And what is the length?
And then with the recursive program, this was kind of obvious. So you have 2 recursive calls, but you do them after each other. And this is the same that you traverse the tree, and when you go up, you forget anything that was below you.
Except just one bit of.
Yeah, you just store the 1 bit, and then you go. So you store the point where you are, you go down, but whatever you stored when traversing the neighbor, the old neighbor, you forget. Okay. So now we go to the next thing. The next problem, proof PSPACE hardness, which is a little bit more difficult.
Let me ask a question. We have length of the tree is just a logarithm of number.
The depth of the tree is number of variables we have here. For every variable, we go one step down in the tree.
No, in general, the depth of the tree is just a logarithm.
Of the number of leaves. So
Yeah,
yes,
but
that's
how many leaves we have?
exponential. Yeah.
And that's why we don't know. Okay, now I see.
So yeah, the time is exponential, but the space is proportional to the depth.
Yeah.
Okay. So yes. Now let us prove p-space hardness. So we start with fix a language A in p-space. And now take a machine that decides this language M. Oh, I forgot to pin the video again. I hope.
Yes, kind of give an intuition why is that the games are connected to the space completeness.
Well, this is a formula game, right? There is a player who wants to make the formula true. He will say the exist symbols.
No, I mean the game.
So we go.
Or something like that.
Yeah, this I will prove later, but we go step by step. We will first prove that this problem is p-space complete. Then we interpret this formula as a game. So there is an exist player, then both players go over the variables. And when we see that this is a game, it becomes easy to reduce other games to this game.
So basically what were saying just a minute ago, it's just our next step after the problem of
Yeah. And now we go here to this grandmother of p-space complete problem. Okay, so let us fix a Turing machine that decides a language in p-space. And now what we need to do is to make a reduction. We need to have an input and map it to a formula, a Boolean formula that says that is true if and only if machine M accepts X. So phi of X, so the formula, this is our reduction. And we know that Boolean formula is true, well, quantified Boolean formula. Phi, which is true if and only if M of X accepts. And the only information we can use about M is that it runs in time, in space P of length of X. So P is polynomial.
Well, basically M accepts X is just the same as the X is in A.
Yeah. M accept X is the same as X is in A. Okay, so how do we construct this quantified Boolean formula? This formula will simulate the middle first algorithm. So we know that there is, with this middle first algorithm, if the extra parameter is 1, so let us make an algorithm and let us call it middle first formula. Middle first search formula.
And the instead of the length of a path, we will be using the number of variables.
No, we will. It will receive configuration graph of Turing machine. We will try to find the path, but then okay. Middle first search formula, and so it receives 2 nodes of configuration graph. So 2 configurations, let's call them C1, C2, and some integer t. So here we get configurations. They are encoded as binary as a list of variables, binary variables. So here it is list x1 till xn of variable. Let's xt. Okay, C is maybe a xk of variables. And then there will be several cases.
So C1
Yeah.
is a list of variables.
Yeah, so it receives it receives two lists of variables and an integers, and it returns a formula that's equal to that's true if and only if these configurations are reachable after. So you can go from configuration 1 to configuration 2 in t steps. So if we follow computation for t steps, at most t steps, formula will be true.
So configurations corresponds to list of evaluation of the variables.
Yeah.
And
Binary variable encoding configuration. All right, so x1 and c of x2, it's a list of binary variables. For each assignment, we get a configuration.
You assume that we can get from the configuration to itself in any.
Yeah. So if we follow this configuration for at most t steps, do we see C2?
Okay.
That's the answer of the algorithm. So result. Oh, I have no space to write this. Okay, I will write it under the. Let's use Python notation. Docstring result. True formula that is true. It's true if starting from configuration C1 in at most t steps and up in C2. Okay, and then here if t is smaller than 1, so it's easy, we can just return a constant. No, not a constant. If t is at most, if t is 0, okay. If t is 0, then return C1 equal to C2. If t is equal to 1,
well, C1 equals to C2, it's predicate, or it's a predicate.
yeah. So we get a bunch of variables and we check whether this is equal to a bunch of variables. We can go in 0 steps from C1 to C2 only if they are equal, if they are the same configuration. If t is equal to 1, then we return. Okay, then we have to use a transition table of the machine. So we will output a big OR, well, a big AND, but just see that it's clear how you can check it. So here we have a configuration. It's polynomial number of variables.
I mean, can we get from C1 to C2 in one step? So
in one formula. It's a formula that outputs whether these two configurations are the next. It is the NC0 Boolean formula of previous lecture.
Yeah.
That checks for one step. So it's actually easy. We discussed it in return NC0 form, NC0 circuit. Well, it's a circuit, but we can transform it to a Boolean formula. So Boolean formula is just with span in 1, and if it's span in 5, then we copy it 5 times, and we get Boolean formula. So here it's NC0 circuit. Okay, and okay. Boolean formula, yeah.
Boolean formula, because NC0 is just equals all Boolean formulas. So let's see.
No, NC0 is not all Boolean. Yeah.
And then C0 is smaller than that, so we can.
Yeah. Cool. Yeah, good point. Boolean formula from NC0 circuit. Okay, and then if t is larger.
And how do we compute that Boolean formula?
Yeah, so in previous lecture, we constructed NC0 circuit to check one step of Turing machine.
Oh,
Yes, it wasn't the proof of Cook-Levin theorem. Now we use this circuit again, but we transform it to a Boolean formula. And Boolean formula is a circuit in which fan out of each gate is at most 1. If the fan out is bigger, then we copy the gate. And in NC0 circuit, we have a constant number for each output. We use a constant number of gates. So the formula is of polynomial size. Okay, so this should be okay. And then if t is at least 2, and now I will write something. It will be correct, but the formula will be too big. But okay, I will write it and then we will fix it later. So if t is 2, then we have this loop over all the states. So we will write for all w, so for all c tilde, we will make 2 recursive calls. We will plug in MFS. Let's abbreviate a bit. MSF. Formula of C1 C tilde with T over 2. And MSF formula of C tilde C2 of T over 2. Okay, so now we have generated a new formula with one more quantifier. So if we run this program for t being exponential, then we will end up with a formula. And the formula will satisfy the equivalence of the reduction. Okay, so the ground call will be, okay, we do it again the same thing, like if machine accept, it will clean up its state, and then we have the start configuration, and then this unique accept configuration. And so when we insert these two configurations, and then with the correct exponential bound on the number of maximal number of configurations, then this formula, this program produces a formula that is true if and only if the machine accepts. So we achieved the first goal. We transferred our problem to a Boolean formula. So do I need to explain this again?
Yeah, it's
Yeah. Okay. So do you agree that the output of this program will be a formula?
Yes.
Okay, that's good.
But just a formula.
Yeah, just a formula.
Size.
That's our first step. We agree it's a formula.
Okay.
Second, let's agree. Can we agree that if the machine accepts, then this formula will be true? And the base call is the unique start state, then the unique accept state, because we assume that there is just one accept state for the computation head. And after it accepts, it cleans up the tape, and we know precisely the tape. So there is a unique accept configuration. So we answered start configuration, accept configuration, and T is this exponential bound on the number of different configurations.
We wanted to be exponential and logarithm and then PSPACE. Okay.
No logarithms here.
Then I'm confused. Why exponential?
Why exponential? Because our machine has, so this is the size of configuration graph we put here. Number of vertices and configuration, which is exponential.
Yeah.
Okay. So we insert this here. And then,
but it's not, if we'll start the exponential amount, we don't get a formula for polynomial size.
no, we don't get formula of polynomial size, but let's first agree that it's the correct formula. Then I will turn it into polynomial size. Yes.
If t is more is equal to 2 or more than 2, we iterate by all configurations, and
Yeah.
do we use the disjunction for all of them?
No, it's a part of the formula. So maybe I should put quotes here. So we create a formula. And then, okay, and here we insert the output. So this is also an encoding of a formula. And so it's kind of a string plus the output of this thing.
But
And why is for all C tilde? Isn't it exists C tilde that part is exist? Why is for all C tilde? Why it's not exists C tilde?
Oh, yeah, good point. Sorry.
yeah, this is why I asked about the
Yeah.
disjunction.
It was, yeah. Sorry. Yeah, my mistake. Yeah. But I was thinking like we make a form, so we do something for all, blah, blah, blah. And then I wrote for all, yeah. Okay, yeah. Okay, and so basically it works for the same reason that middle first search works. So if there exists an accepting path for the computation, then there must exist a configuration in the middle for which we see this just by the requirement here. It's kind of open. Okay, now so we obtain a formula that is equivalent to the machine accepting. But our problem is that it's too long. So where is the problem? It is that we make 2 recursive calls. It's bad because then so each recursive call makes the formula longer. Like before we were reusing the space and we just have to think about the space used by 1 recursive call. But now here we don't gain anything by it. So it's exponentially long. So we will need to make 1 recursive call. And so the way we do this is by using additional by a for all quantifier. So we will make a quantifier over 2 variables here. And then we will check whether, okay, I will just write it, which give me a minute, and then it will be clear. So this step we will write, so there exists C tilde, and then I will say for all pairs, let's call them D1 and D2. They're also configurations. For all pairs, we will have implication D1, D2 equal to C1, C tilde, or D1, D2 equal to C tilde, C2, implies, and then this thing here. Yeah, sorry, without quantifier. So then implies this thing.
Don't we have 2 recursions?
Sorry, yeah, 1 recursion. Yeah, I can actually write this. Yeah, so thank you. MFS formula
And what is with the
D1,
after C1?
D2, and D over 2.
Or D2.
Yeah. So that's the magical trick. So what is this formula doing? So we will check all states D1 and D2. And this implication needs to be true. Implication can be written with or and negations and so on. And so if D1 and if this is true, if the first thing is true, then this must be true by implication. So this formula is, so this is a formula of the form, so X implies Y, So this is the formula, right? And this is true if and only if not X or Y. So it's kind of same notation. If, I hope, right? So either X is 0, but if X is 1,
that's
then-
right. I just using the.
yeah, this is the idea. So we need to make two checks. And we will do them by creating a new variable using a universal quantifier, and then check over this new variable. And the check is non-trivial when this new variable is equal to the input of the first check or the input of the second check. It's idea.
How
Yes. So what is here the problem? We need to make two checks, and this check makes our formula too long because we use two recursions. We need one recursion. So before doing the recursion, we add a universal quantifier. And then we make sure that here is the check happening, but we do it in an abstract way, this check.
So we show that there is a way from
Yeah,
C1 to C tilde, and there is a way from C tilde to.
yeah. So we create new variables and we do the recursion on the new variables. And then we make a universal quantifier to use this new variables twice for our check. So this check, this implication is non-trivial. Okay, let me write extra brackets here. This implication is non-trivial either if the new variable is equal to the input of the first check or the input of the second check. Then we have a 1 here, and it means we need to have a 1 here. And if variables are not, if D1 and D2 are different from both of these inputs, then we don't need to check anything. And so in this way, we have written a formula using one recursive call.
Okay.
So if we replace this line by this line, then we are good. We have a formula that's equivalent and is of polynomial size because we have the recursion tree is just a path of length n.
So any D1, D2 will look like any D1, any D2.
Yeah. Yeah, so these are basically two equalities, but I've written them, but that was clear, right? Okay. So that means we have proven that TQBF is p-space complete. Okay. So let me quickly check the seminar whether there is anything about
What is the synthetic of the size of the formula?
Okay, there are no questions about formula for generalized geography, so that's okay. And your question, what is asymptotics?
Of the size of the formula.
Yeah.
So,
Okay, so the Turing machine runs in space P of length of X. It means that each configuration, the size, is P of X. And the number of variables that we need in each recursive call. So we just have to look here. We need 1, 2, 3 new variables that will be added. And then here, again, we check these variables. So here we add order, length of configuration things. And then in total, we make number of recursive calls is 2 to the power order P of n for the size of configuration graph. So it will be the size of formula will be the square of P of n. So this polynomial square.
And what was the size of the formulas when we had it two recursive?
But then it is 2 to the power P of n or something like this. It's P of n times 2 to the power P of n. It's too much with this. It's not a polynomial time reduction.
So yeah, we have exponential size here because because the graph of the states.
Yeah, so you look at the recursion tree here, and it's a binary tree, and the depth is the logarithm of the size of configuration graph.
Which is polynomial.
Yeah, so the depth is polynomial, but every recursive call, the number of leaves is exponential, but each recursive call adds something to the final formula. This part is added, and okay, and then the bit there. So exponentially many times our program or recursive calls will add something to the final formula.
Something polynomial.
Yeah, something polynomial, but
Exponential times. Okay.
yeah, and so it's exponential size. But here it's not happening because we make one recursive call. So the full recursion tree is just a path of length, length logarithm of size of configuration graph. So we have a formula of length quadratic and P of n, where P is the size of the original Turing machine. This paper.
So I maybe understood. So basically, what is happening is that in that case we had something like a binary tree, and then that recursion we went here, and each level of the tree we have two options, two recursions, and it's like something like two to the power like or order of n times the polynomial of n. Yes, and in that case we have not a tree. We have just in every layer we just went to the one.
Yeah.
Oh, okay, and then it's just the length of the path, and it's a polynomial. Well, maybe it's squared, but it's not interesting. It's just poly of n, and that's PSPACE. Okay, now let's see.
Okay. So more questions.
Are there many online students?
4. I don't know in what state they are because cameras are off. But you heard some questions, so at least one was awake till half of the lecture.
Let's hope that they are in the second state.
Yeah, but the total watch time on YouTube was quite good, so it's people are watching. Okay, I will tell Nikita to start at 7:50 the seminar, so you have 10 minutes for break, and then 10 minutes less of. Okay, bye. See you.
Bye.